Hello, my name is Thomas Theiner, and I've been doing research on ultra-thin films for solar energy applications. For some quick background on semiconductors and solar cells, as many of you probably know, a semiconductor is a material with distinct non-overlapping valence and conduction bands. There's a band of states, the valence band occupied at equilibrium, and then above that there's an unfilled but allowed band of states, but then between that you can't have those states filled. And one way you can excite electrons up from that valence band up into the conduction band is by absorbing photons, and that's the basis of solar energy, is basically extracting energy from that process. Another way you can get a more permanent population of electrons up in the conduction band, or holes, just unfilled states in the valence band, is by doping them. Doping the semiconductor, you can add an atom with a higher valency, like phosphorus and silicon, which will basically just add another electron into the material, which will fill into the conduction band. Or you could add something like boron that has a lower valency, that'll just leave a hole in the valence band. Significant about these doped semiconductors is what happens when you put them up next to each other. So the N-type side, the one with the higher valency atom added, that'll have a higher nuclear charge counterbalanced by extra electrons, versus the P-type side having lower average nuclear charge counterbalanced by more holes. So charge neutrality says that there should be no intermixing of these carriers at the interface, because that's going to violate charge neutrality, because the nuclei can't move. However, you also aren't going to have a perfect sudden concentration gradient of these carriers. That's just diffusion-wise, that's not going to be favorable. So they do diffuse a tiny bit until that electronic driving force becomes too much, and that creates some electric field at the interface. And this is enough to really push electrons towards the N-type side and holes towards the P-type side. So what's significant about this p-n junction is if you have an electron-hole pair, like you'll get when you excite an electron, you'll force the electron to go one direction, you'll force the hole to go the other, but since these are opposite charges, that really forces current in one direction. So effectively, p-n junctions will allow you to transfer the energy from absorbing a photon into electrical power. A more useful way to conceptualize this process would be with the diagram that I have in my poster showing the different energy levels of the two different materials. So basically, you would have an adjustment of the energy level of the conduction band and valence band of the two materials with respect to each other when you have this interaction. In this research, we're not really seeing exactly a p-n junction. However, we're still modeling out materials in terms of these relative energy bands, because that's fundamentally what you need in order to have a photovoltaic device function. I think the only other important bit of background information I need to give is on XPS. This stands for X-ray photoelectron spectroscopy, and this is just a technique where you fire an X-ray beam at a sample, a constant energy, and you measure the kinetic energy of the electrons you get off of it, and you just subtract that from the initial energy, which is known, and that gives you the binding energy. You get out spectra with peaks corresponding to where you see large clusters of binding energy. This tells you where the different core levels of electrons are, and also even out to the edge of the valence band. And this is useful because this is precise enough that different chemical species have distinct binding energies, because the bonding character changes slightly, and this changes how tightly electrons are held. And you can measure all the way out into the valence band, and that'll tell you, what's the energy of the edge of the valence band relative to the core levels of the sample. And then if you get core levels at a heterojunction sample where you have two films on top of each other, and then you also know where the valence band lies in each of the materials relative to the core levels, that can allow you to figure out this alignment of bands that we're saying is so important for determining how a photovoltaic device acts. So for my work, I work in a group that focuses on atomic layer deposition, or ALD. This is a process where you expose a substrate to two precursors alternately, and basically they react in a self-limiting way. I think this is summed up pretty well on the diagram I have on my poster, where, like on that one, you have TMA encounters the substrate. One layer adsorbs onto it, but then it leaves a bunch of methyl groups sticking out that other TMA molecules don't really want to interact with, so it's self-limiting in that way. And the same thing happens when you put in the other precursor, which is just water. And that reacts to form some alumina, and then you repeat this over and over again and slowly grow up that alumina layer. We didn't grow alumina in this study, but we did grow molybdenum oxide and titanium oxide. Many different thicknesses of molybdenum oxide were deposited. We went 15, 25, 50, 80, and 120 cycles. This creates thicknesses ranging from just a bit over one monolayer to, I want to say, somewhere around 10 nanometers, significantly thicker. And then these were sent off to be tellerized where they were annealed in a dilute tellurium atmosphere, and this turned them into molybdenum telluride instead of molybdenum oxide. So why do we care so much about this molybdenum telluride? It has a couple of properties that are really of interest to us, and it's not super well studied. First of all, it absorbs visible light very, very strongly. These, even just a few nanometer films, appear basically black, which is really unusual. And it also has a band gap right in kind of the sweet spot for photovoltaics. It's around that of silicon, which is the most commonly used photovoltaic material by far, whereas it's around 1 electron volt. And this is at a level where you're not going to be letting a lot of radiation through that you don't need to, but you're also getting a significant excitation event when you are absorbing photons. So on the film chemistry side of things, the most interesting thing we saw is that you do have a slight reduction in the amount of oxide you see on these samples after you expose it to the precursor that we use to deposit titania. This isn't terribly surprising. These precursors are, by definition, they're reducing agents. They exist to be oxidized, but it is interesting to document. Really, the main takeaway from this work are these band diagrams that we made looking at the valence bands in XPS. And you can really see that for these thicker samples, it looks so far like for the thicker samples, you're getting more of a conduction band offset and more of a valence band offset. For those of you familiar with solar cells, you may see that and be thinking that looks like a greater open circuit voltage you're going to get. And that seems to be the case. It seems like there is a stronger potential at the interface for these thicker samples. Of course, we are going to test more samples to confirm these findings, make sure that this is not just a fluke that's within the margin of error. And going forward, this is going to be very useful to inform further study on the behavior of carriers in molybdenum telluride and TiO2 heterostructures. The plan is to apply transient absorption spectroscopy, which allows you to track how electrons move to different energy levels throughout the sample in real time, basically.